So with Bohr, there's a couple things we got to talk about real quick. First, the main thing is light, right? So Bohr uses light to learn more about the atom, and light, remember, is just a small part of the electromagnetic spectrum. So you can see the picture here. You've got non-ionizing energy over here with low energy. Over here to ionizing energy, this is the dangerous stuff, X-rays and gamma rays. Everything below that we'd consider not damaging, right? So cell phones fall here in the middle. Which is why moms and grandmas got all freaked out and they said, "Oh, cell phones are giving everybody cancer," and we're not seeing that because it's non-ionizing energy. But the shorter your wavelength, you see as we go from left to right along here, the shorter your wavelength, the more energy it is, right? As the wavelength changes, the type of stuff changes, right? It goes from radio waves to microwaves to infrared waves to visible light to ultraviolet and so on. So different wavelength is different energy, and that's a key idea, right? You should read through all that stuff, right? But as this wavelength changes, you're going to get a different amount of energy and a different color is how we perceive that, right? Some terms for us, we've got wavelength, frequency, and then the speed of light. So the speed of light is constant, but as the wavelength and the frequency change, or as the wavelength changes, the frequency changes back and forth, and the amount of energy will change, right? What we have to look at is this picture right here. So when you burn hydrogen, you get these four bright lines. If you spread those out with a prism, you can see these four different bands. There are other bands outside the visible spectrum, but there's these four that we can see. And when Bohr burned neon, he saw a different color. When he burned krypton, he saw different colors. But you always got the same color. That's the flame test lab that we did, right? And that means that those electrons exist in specific energy levels, right? Because if I'm going to get the same color emitted all the time, that same color emitted all the time means that that same amount of energy was transitioned all the time. So if you imagine going down the stairs, you're releasing the same amount of energy because those stairs are in the same place. Well, imagine if the stairs were moving. If the stairs were moving, and I don't mean like an escalator all going in together, I mean moving with respect to each other, you would be releasing different amounts of energy all the time. So your colors would be different all the time. And that's not what we see. We also don't see everything burn as a rainbow. We don't see all the colors released because the electrons can't just exist anywhere. If it was a ramp where the electrons could be anywhere along that ramp, then you could release all the colors and you would have a rainbow dinosaur thing, right? You'd have a rainbow where all the colors are released. So since we only see these specific colors, and we always see that we never don't have the green line or don't have the red line, and the red line's always right here and the green line's always right here. That means that those electrons can have specific energy jumps, and those electrons can have specific energy jumps, and that means those electrons need to exist in specific energy levels. And this is the baby version, the beginning of the ideas of quantum energies and stuff, right? So Bohr said, if an electron jumps up to a higher energy level, it's going to fall back down to a lower energy level. When it does, it's going to release light. That light only and always have certain energy levels, right? Only and always is kind of important there. And so we see all the different combinations here, right? So you can jump from like the third energy level to the second, from the fourth clear down to the first. The bigger that drop, the more energy, and the closer that color would be to a violet or an ultraviolet or an X-ray kind of thing. The less energy, the more it's towards a red, an infrared, a microwave kind of idea. And how that math works and stuff, we don't need to worry about at our level. But it is important that these are quantized energies. Quantized, they're stairs, right? The amount of energy is here or here or here. It's not in between there. It's not anywhere down the ramp here. It's somewhere on one of these stairs. And the distance between those stairs can be different for different atoms and all that kind of stuff. But the electrons have to exist in specific energy levels. The animation that you can look at right here is really helpful. And then you end up with an atom that looks like this, where you still have your nucleus that is small, dense, and positively charged in the middle. You have your orbitals outside of that, and that's where the electrons can exist. And so it's not classical physics anymore that Rutherford had a problem with, saying, well, a charged particle in classical physics releases energy. Well, this isn't classical physics. This is now quantum physics. And so those electrons can only exist in specific energy levels. Bohr's wrong about the shape of them, right? They look like the SPDF stuff we looked at earlier this year, but he was right about the energy levels being the electrons existing in energy levels, right? So hopefully that helps.